Right, so our final speaker today is Pavlo Mazurovsky. He'll be presenting depth and depth-based classification with the R package DD alpha.
Okay. Good afternoon, ladies and gentlemen. I would like to present you our common work with my two co-authors, with Alexei and Rainer, where basically it's about implementation of some methodology, some statistical methodology, which is kind of 40 years old, which is called data depth, or more fully statistical data depth function, which has been theoretical before, since several years, and then due to, some developments, it took decades till the algorithms have been developed. It took decades till we had computers powerful enough to compute these things. But indeed, this is a nice methodology which may give some interesting insights while treating data in non-parametric, distribution-free, and often geometrically driven way. And we implemented this methodology in our package, which is called DD alpha. Well, at the useR conference, I have a good reason to assume that you are familiar with R and you know how to use package. This is why I decided to put main focus of the talk on the methodology. So there will be some mathematics, a bit. And first I will speak about what is the method, as data depth as a method, as a statistical method, and then how you classify with this data depth. Then we'll take a look at the package and we will get familiar with some problems you can face if you try to do statistics with data depth. So the setup, you have a data set, like just an arbitrary data set, and you pick a point in the space. This is this I don't see it, red point here, yeah. And what you want to say, you try to define how deep this point is in your data set, in your data cloud, and you try to define it like not to take in any assumptions, not to speaking about distributions, but just using the data itself, like to let the data speak. And basically, what you say is just some mathematics, some mapping, where you have a function which assigns to a point a value between 0 and 1. It assigns 1 or something close to 1 if your point is deep in the data cloud, and it assigns something which is rather 0 if your point is far from your data set. Okay? So clearly there are very many ways to define this kind of function. This is too abstract. So that's why there was some axiomatics developed which said that there should be some properties which are fulfilled by this kind of functions. There should be a affine invariant, which means that you can basically apply any invariant transformation to your data set, and the data depth will not change. It should be vanishing at infinity, which is kind of reasonable. If you move far from your data set, the depth will go to 0. Depth should be decreasing if you move from the center of your data cloud, and the contours of this data depth function should have nice shape. So to give an example how it may work, this is the historically first notion of data depth defined by John Tukey. Well, if you see, it's like you try to cut off the smallest probability of your data by a half space, keeping the point for which you calculate the data depth in this half space. Well, if you speak what is probability of the data, basically if we speak about a sample, it's just a portion of points of your sample, right? So let's go back to our example. So we look at our red point. Now we want to cut off, we want to define a half space. What is like half space? Is just part of the plane cut off by a line. And we want to find this half space which minimizes the portion of points in itself, but contains this red point. No, it doesn't work. So red point on the boundary. So we go through all possible half spaces until we get some minimal probability mass, some minimum portion of points in one of the half spaces. It's 13, so it defines our depth. So for example, if you take another point, like the point which is rather on the fringe of the data, it should be, I don't know, somewhere here. So for this point, clearly it's further from the center of the data. And if we'll try to cut off as few points as possible, we'll cut off 3 points only. So we can say that then the point is less deep than the previous one. And actually we can compute it for each point of the plane, right? So these were not, these 2 red points, they were not from the samples, they were just arbitrary points. And we can then evaluate this depth function for each point. And we can then visualize the depth function itself. So for example, it will look like that, and the red points you see on the surface of the function, these are just the projections of the points of the sample. For them, we can evaluate the depth as well. So as you can see, it may look somewhat ugly, but indeed this is really what we have if we have a data set, right? So without making any assumptions, it's purely our data. And in fact, there are some applications, there are many applications. As for an example, you can do multivariate analysis, you can do statistical quality control clustering, you can test for location, scale, for symmetry, you can do outlier detection, risk measurement, you can even do robust linear programming by that, or stochastic linear programming, and there are further ones. I think I've forgotten the one by me. You can impute missing data with that as well. And one of the most developed applications is the classification, the supervised classification of that data. There are many works on that, so I will try to briefly say you how you do depth-based supervised classification. Well, here is the setup. The main point here is that you do supervised classification. You have training sample where you have only two classes, right? So you have two classes, and theoretically there exists some ideal rule here, which you never know because you have no knowledge about the process from which your data come from, and you would like to guess it. So how do we classify? This is our training sample. We have two classes, class 0, class 1, of the points in some d-dimensional space, which belong to, where we have m points from class 0 and m points from class 1. What we do? Well, we know how to, if you have one data set and one point, we know that we can calculate depths of this point in this data set. So now we have two classes. We can calculate depths of each point with respect to each of the classes, right? So we do that with each point of our training sample, right? So here I've simulated just two normally distributed classes in dimension 2. What you do for each point, for each blue point, and for each red point, you compute data depths. With respect to blue sample, it's one value. With respect to red sample, it's another value. So you have two values, you have two coordinates. You can put it on the plane, and you get a picture like this. And, well, basically you can see that here there are some blue points, here in the bottom, and here on the top right there are some red points which are rather scattered. And then you can try to separate them in this space. What is interesting here is that whatever is the dimension of the first original space, of the space on that side, whatever is the dimension of this data, if you have two classes, this plot is always two-dimensional. So you really can see what you are classifying, what you are doing during your classification. You can observe it. So we pick arbitrary rule. I will speak about a rule a bit later. And a parabola, like very simple rule. We will learn it in some primary school, I guess. And then if you have a new point which you have to classify, you just compute its depths in each of two samples. You have two coordinates. Then you can also get this point on the plane, on this plane. And if this point is like on the left of parabola, you say, okay, it's blue class. If it's on the right side of this parabola, it's red class. And if you look at actually which classification it gives in the original space, you'll get something like that. So the solid line, so I don't know whether you see, you may see only one line, but there are actually two lines. The solid line is the line induced by the rule we created. And the dotted line is the bias rule, the ideal classification. And you can see they are kind of almost overlapping. Okay, so now let's take something which has more data. It is also real. It's the Pima Indian diabetes data set. And we try to apply this method. And now we try to create, well, how we created this parabola. It's, well, we cannot always separate this parabola. We have to create some classifier. And here we'd like to suggest you the classifier which we call the DD alpha procedure. This is some inductive procedure and heuristics which constructs a quite interesting rule in this DD plot. So if we compute the depth value of each point of the data sample having 7 dimensions in each of the classes, we get DD plot. You can see fewer points because this, you have seen the Stucky depth is discrete. So basically there are many points which are overlapping here. But it's not bad because we already can see some pattern. So what we do further, we do extension of this DD plot. We just, what we can say in machine learning, we apply polynomial kernel of order 2. Or we just use, you know, like all the possible polynomials of order 2. There are not that many, right? So you have only, like we have original two depths, depths in the class 0, depths in class 1. Then we can take their product, squared one and squared second one, and that's it. So now we get 5 features in our data. So this is the same plot you've seen before, just in a 3-dimensional view. So what we do then, we take each pair of these 5 features, and we try to separate by the line, by a line which goes through 0 because in the point, at the origin we cannot decide to which class to assign an observation. We try to separate by minimizing empirical risk. This is extremely cheap. This code's only sorting the points, which has complexity n log n. And we do it like for all possible pairs, and we choose the one where the empirical risk is minimized. By that we have kind of two extended dimensions of the data. Now we can do foldering. We project the data onto one line, and now we have one dimension again. And then now we have kind of, we've chosen two features. There are still like 3 features left. So now we try to put one of the features to the one we created, to the new one we created, and we try to separate by minimizing empirical risk in this plane again, and we choose the best feature again. And we continue till we are improving the classification, till we are, our error rate is getting smaller and smaller. So that much about classification. Now let's say just several words about the package itself. So basically, if you use the data depths and you try to classify with data depths, you get a classifier which is affine invariant, which is actually very nice because many of the classifiers you may think about, they are not affine invariant. It is robust. Also a property, if you have a point which is really on the fringe, the classifier will be stable for most of the depths you apply. It's non-parametric because we do not have any parameters in our models, so the construction is completely taught us by data, and is distribution free. Well, we don't have any model at all. We don't assume any distribution. Well, so we just tried to implement all this kind of methods, and we get some problems because as the works were very theoretical, there were no many implementations. There are very different languages, different interfaces, well, different formats of data or of input you have to get. So basically you have just a variety of things and you don't know what to do with it. And there were no one implementation of depths and depth-based classifiers under one roof. So what we did just in this package, we summarized the work of researchers, the work which already existed. We just programmed it and gave some nice API, our API, to use it. And this is shortly structure of the R package. Well, it's a bit reduced for understanding. So once more what we do, we take multivariate data set, right? Then we compute the data depths to get the ddplot. Then we separate the rule in the ddplot, and okay, the package gives possibility to get some statistical inference in more or less automatic way. And in fact, the main challenge when computing data depths is what I started, with which I started my talk, is this transformation, the depth transform. I don't know, I didn't see it in my own. So the depth transform, if you want to compute the depths of multivariate data, because it's actually very time consuming and there are not many algorithms available. So that you so that you can imagine, there are very many possibilities to define this data depths. It depends on your needs. There are approximately like, I don't know, 15 or something like that depths is defined. 7 of them we found most reasonable. So we implemented them in the package, and this is the view of this depth function for just some data set with outliers on the bottom, which you can see. And on the lower pictures, you can see the contours of this depth function. Right? So these are like Mahalanobis depths, projection depths, spatial depths, Tukey depths, Zenoid depths, simplicial depths, and simplicial volume depths. Well, I don't go into detail, of course. And here, for all the 7 depths, here is the computation time. Well, as you can see, even for tiny data sets, it can be really quite challenging. So this is the time you need to compute data depths of one point with respect to a data set. Yeah, so kind of data depth is a nice function. It tells you many things about the data without any assumptions about distribution, about doesn't have any parameters, but you have to pay for that with computational burden. And for the depths we've seen, this is the half-space depth, the second one. Well, this is the red dotted line, the red dashed line. You can see that, for example, both scales are logarithmic actually. So basically, straight lines do not say us anything good, right? So if you have 500 points in dimension 5, you will wait like around 1 hour to compute it on a computer like this. But still the methodology is used at least for some of the data sets. And so as this is very complicated to compute, this is why when implementing the computation of these depths, we did not implement only exact computation, we implemented also approximate computation, which goes very fast. Well, way faster. You can do it with thousands of points in dimensions up to 15, 20, and even higher. Okay, so now I'll just have to summarize my package, our package in the half a minute that I have. It's a package which is already on CRAN since like 3 or 4 years. It provides exact and approximate computation of 7 depths. It gives possibilities for depth-based supervised learning. It supports not only multivariate data. I was speaking only about multivariate data, but it also supports functional data. Well, it has some outsider treatments. This is a topic I didn't touch because, well, sometimes depths do not work for several kinds of observations when you classify, so you have to treat them in a special way. It has built-in procedures for statistical inference. It has data sets so that one can play around and take a look how it works. And it has procedures of visualization. Basically, to create all these pictures, usually you need like one line of R code. So thank you for your attention, and we'll be glad to open your questions. Yeah. Yeah, so the question is that, in fact, to classify, like not only to train, but also to classify, we need the entire data set. And this is kind of consuming, at least in terms of memory. Well, yeah, this is true. This is true. So there is, well, there are two things I can say. The first thing is that, in fact, for the moment, you cannot say apply these methods for big data, like no way. Well, it will, and I don't think it will be done in like several years which follow, but maybe you can change methodology. Second, sometimes, well, you can try to find a way to store the depth function itself, then you don't have, so if you develop some structure to store the function itself, then you don't need to store the data set, for example. So that's it.
So yeah, I'm sure the speakers will all be sticking around afterwards if you have more questions, but let's just thank them all one more time, and thanks for coming.